All right, so today we're going to talk about parametric equation in calculus. So in the previous lesson, we talked about what a parametric equation was and why they're useful. And today we're going to show you a few things that will help you specifically when it comes to the motion of an object. All right, so first, let's say that we have a curve C that's defined by the parametric equation x is equal to t squared and y is equal to t cubed minus 3t. All right, if we're trying to find the derivative with respect to time of x, well, that should be easy for you, right? This would be 2t, right? And for y, right, y being right there, if I take the derivative of that with respect to time, let me stop saying time with respect to t, because I don't really know what t is at this point. Should be 3t squared minus 3. Right, and if we're going to try to find dy dx, right, the derivative of y with respect to x is actually very simple, right? What we would do is that we would divide dy over dt, and we would divide that by dx over dt. Now, if you do that, right, if we keep the denominator the same, and we multiply, and we flip the bottom part, essentially what we would have is dy dx. So for this specific function, dy over dx would be the same thing as 3t squared minus 3 all over 2t. Okay, it'll be useful because we're going to use it quite a bit in this lesson and beyond, for you to remember that any time that you have taken the derivative of y with respect to t and x with respect to t, that dy dx would be equal to that. So make sure and try to memorize this equation. All right, now if we're talking about the second derivative, all right, of y with respect to x, remember we have this parametric equation, so we're going to have to do a little bit of work. This is the formula. This is another formula you need to memorize, okay? Now, we're not deriving that yet, and we can show you that in a different video, but you need to, for now, just memorize it. So what we're going to do, especially because it's asking us for this, right, d over dt, well, that stays the same, nothing different. Dy dx is what we found previously, so we have 3t squared minus 3 all over 2t divided by dx dt. And remember, dx dt is right there, so this is 2t. Right, so after that, there's going to be some simple, well, before I simplify, I'm going to have to take the derivative with respect to time, or t, excuse me, of this function right here, right? So to take the derivative of that, I need the quotient rule. So I have the low times the derivative of the high minus the high times the derivative of the low. So low d high minus high d low. All over the bottom square, so 2t squared would be 4t squared. All of that over 2t. All right, well, when we simplify the top here, we would end up with 12t squared minus 6t squared plus 6 over 4t squared. Now, if we divide this by 2t, and I keep change and flip, right, the 2t normally would be right here if I'm dividing, but because I divide by a fraction, I can actually multiply by 1 over 2t. So this is going to be 6, well, this is going to add together, right, they're like terms. So it's going to be 6t squared plus 6 all over 8t cubed. Of course, if you notice, all of these are divisible by 2, so you can simplify this a little bit further. So this is 3t squared plus 3 over 4t cubed. All right, so that's the second derivative. All right, on D it says the curve C, all right, the curve C is this one, the one that we had up here. That's how curve C is defined. All right, it has two tangent lines at the point 30. Now, at that point 30, this is X and Y, okay? And this is why this is going to be a little bit trickier than normal. Where the curve crosses itself, find the equation. So again, we're trying to find the equations of the tangent line. All right, now the problem is that my curve C is defined with a parametric equation. All right, so it's not going to be as simple as just finding the slope, finding the point, although it is. So we're going to have to just convert this 30 into something that has to do with t. Okay, so first, let's see. According to that function, let me see, x is equal to 3, right? And I'm going to write the equation here so I don't have to keep looking up. So according to that, x is this, y is this. All right, so if x is equal to 3, and I plug that in into that equation, so that means that 3 is equal to t squared, which means that t is equal to plus or minus the square root of 3. I guess I could have done it like that. You could also do it with the y. Very interesting. So if y is 0, I could have used 0 is equal to t cubed minus 3t squared. 5 factor of t. I put a 3t squared. That's not true. Did I miss? Right? Yes, I did. Just notice I didn't write that correctly the first time. I'm sorry. There's not a 3t squared. So I'm going to factor out a t. So this is going to be t squared minus 3. So this one, t, which really is going to give me the same thing. I would have 0 and I would have plus or minus the square root of 3. But notice that the 0 really doesn't matter because at t is equal to 0, nothing's happening. Okay, so now what we're going to do from that point, okay, so at t is equal to plus or minus the square root of 3, those are the only t's that resulted in the point 30. So now I have the point. I already have the point. I already have that. It's 30. I don't need that, right? But what I need now is I need to figure out the derivative with respect to, I need to figure out the derivative at the square root of 3 and the derivative at the negative square root of 3. Okay? Okay. So for this one right here, the derivative of y with respect to, let me see. I think I'm getting all jumbled up here. I am, sorry. The derivative defined, at t is equal to the square root of 3 would be the following, right? So I'm going to use this right here that I found earlier to figure out the rest of this. So I have 3 times the square root of 3 times, square, minus 3 over 2 square roots of 3. So this is going to be 6 over 2 square roots of 3. And if I rationalize the denominator, that's just going to give me 6 times the square root of 3 over 6, which is the square root of 3. All right, so again, the slope at 0.30 would be the square root of 3. So we're good there. All right, so sorry I sort of made a mess of that question here. But since we have another point, so I'm going to have to figure out the derivative at t is equal to negative square roots of 3. So it's basically almost going to be exactly the same equation, except for on the bottom, I'm going to have a negative square root instead of a positive. So using the same kind of steps, rationalizing the denominator and everything, that's what I would get. Okay, so therefore my tangent lines would be equal, well, the top one would be equal to y minus 0. I guess I should probably write that just in case. Well, let's not. Y minus 0, so I'm just going to write y is equal to the slope at that point, which is square root of 3. Then x minus 3 here. And the other one is just going to be y minus 0 again, but the slope is going to be a negative square root of 3. And then we have x minus 3 again. So those are my solutions. All right, so let me go over that again because I did sort of make a mess out of that, or I probably told you wrong there. If you're trying to find the if you're trying to find the equation of a tangent line, again, you need a point, you need a slope. The only problem is that my derivative is defined in terms of t. So I can't just plug in 3, 0, or even 3 or 0 into my derivative. I have to plug in a t value. And that t value is either going to come from this one or this one. It really shouldn't matter which one you use, but it should come from either one of those, right? That you should get the same answer no matter how you do it. So once you have done it, okay, then you can, if you wanted to, okay, then after that, then you can just plug in the square root of 3 for the derivative and the negative square root of 3 for the derivative, and that will give you your slopes for the tangent line. Okay, and right here they're just telling you a few more things. Specifically, there is a second derivative and the third derivative in case you would need it. Okay, the second derivative we have just done. All right, so let's go to example number 1 now. Okay, on example number 1, all right, first we're going to do kind of what we did on the first, on 8.1, just the parametric equation notes. We have to write a rectangular form by eliminating the parameter. Now, if you remember these are a little bit funny because what you're supposed to do is I'm supposed to write this. I'm supposed to eliminate this parameter, which is theta, right? I'm going to divide both sides by 2. And on this side, I'm going to do the same, but I'm going to divide by 3. So I have this. Now, as I said in the previous video, cosine squared plus sine squared is equal to 1. So that would allow me to square both this. See, cosine squared would be that, sine squared would be this. All right, so I'm going to square both sides. So I have x squared over 4, and this will be y squared over 9. And that's going to be equal to 1. Okay? What that would look like if I were to graph it is I have a minor axis, right? This right here, the square root of 4, which is 2, would give me the minor axis here. And the square root of 9 here would give me the major axis. And it's only the major axis because it happens to be longer. All right? And when you connect the dots, this is going to be an ellipse. Okay. So as that says, what shape did you get? Well, I just said it. We got an ellipse, right? Says find the slope of the curve at pi is equal to pi over 3. Excuse me, theta is equal to pi over 3. So what we're going to do here, all right, if I want to find the slope, remember, how do I find the slope? I have to take the derivative. Okay, so I'm going to have to take the derivative first. I have to take the derivative with respect to y. Excuse me, the derivative with respect to theta. The derivative of y with respect to theta, and then the derivative of x with respect to theta. So if you look at this equation right here, y is this. If I take the derivative of that, then I would get 3 cosine. The derivative of sine is cosine, right? If I take the derivative of 2 cosine, I get negative 2 sine of theta. All right, so again, to find the slope of the curve at theta is equal to pi over 3, Now I have to figure out what is dy dx. Well, dy dx is 3 cosine of theta over negative 2 sine of theta and I have to figure that out. I guess I could have written that as cotangent, but I think it would be easier if I write it like that. All right, so this is the same thing as 3 cosine of pi over 3 over negative 2 sine of pi over 3. This is 1/2. This is the square root of 3 over 2. Let's see. Well, that's going to cancel, so I don't need that. So this is basically going to be 3/2 over the negative square root of 3, which is 3 over 2, negative 2 square roots of 3 now. All right. And then if I multiply top and bottom by the square root of 3, that's going to give me, and again, all this after that point really you should be able to do on your own, but that's going to be negative 6 here. So that's going to give me a negative, I'm going to write it as square root of 3 over negative 2, or negative square roots of 3 over 2. Right, so that is it for that. So basically the new stuff happened between here and here. After that, then it became just algebra. All right, so now we're going to write the equation of the tangent line through this point. Okay, so what we're going to do here, and what through this point, they're talking about, well, actually, I don't know what this point is, but I do know that theta is equal to pi over 3, right? So that's what we're going to do, similar to the last one, right? To write the equation of a tangent line, I need a point and I need a slope. But on this one, they don't give me the point. They give me theta, or the parametric parameter, if you will. So what I have to do first is I have to use the original equations, and I have to plug in the pi over 3. Oh my gosh. Okay. So this is going to be 2 times a half, which is 1. And this is going to be 3 sine of pi over 3, which is going to be 2 times the square root of 3 over 2, I believe. Oh, and I put a 2 there. That should be a 3. So this is going to be 3 square roots of 3 over 2. All right, so I'm going to take a little pause here. Well, actually, I think I can finish. Okay. So here's the deal, guys. I have the point. I have the x coordinate, which is 1, and the y coordinate, which is 3 square roots of 3 over 2. Do I have the slope at that point? Well, I do, because I found it here. Right, so this was a little bit different than we did last time. We already know the slope at theta is equal to pi over 3, which is the same thing as the slope when x is equal to 1 and y is 3 square roots of 3 over 2. All right, so I'm pretty much done. At this point, I just have to write, and I can write it here, the slope, or m, is equal to negative square roots of 3 over 2. So I'm able to write my equation of a tangent line. So I have y minus 3 square roots of 3 over 2 is equal to the slope, which is negative square root of 3 over 2 times x minus 1. Right, and that's it for that. All right, so let's move on to the next one. Now, I will take a little break here, but just give me a second. All right, so continuing on with what we're doing here, so let's go to example 2. So on this one, it says the final points, if any, of a horizontal and vertical tangency to the curve. All right, so what that means to you, if you remember from even Cal 1, all right, we have a horizontal tangent when our derivative, and really, in this case, it may not necessarily apply just like this, but basically when the derivative is equal to 0, all right, so I'm going to call this when dy dx is equal to 0, or if it's a vertical tangent, then that's when dy dx is equal to what I call 1 over 0 or undefined. Right, so it could be either one. So this one, what makes, again, this interesting is that this is a parametric equation. All right, so the parametric equation is given to you by x is equal to t plus 4 and y is equal to t cubed minus 3t. So again, to figure out dy dx, if you remember, and this is what I put at the beginning, that's what we're trying to figure out. We have to have dy over dt in this case, and dx over dt. All right, so we have to figure that out first. So to take the derivative of y, so dy dt is equal to 3t squared minus 3. And dx dt is going to be equal to 1. All right, so I'm just taking derivatives of this. So this one's actually not too bad, because if I divide 3t squared, right, so to find dy dx, I just have to divide those two derivatives that I found above. 3t squared minus 3 over 1, which is just 3t squared minus 3, right? So I have to set this equal to 0. Now, hopefully we all understand now that this is not going to be undefined, all right? There's not a point on a square function or a quadratic function that will not be, that it's basically smooth throughout the whole thing. There's no sharp points and no discontinuity. So I am not going to have a vertical tangency, but I will definitely have a horizontal tangency. All right, so I'm going to go ahead and solve for t. Many ways to do this. I'm going to add the 3, divide by 3, so I get this. And if I take the square root, I'm going to get plus or minus 1. Okay? So now what I have to do, all right, so again, because he wants to know all the points, okay? Now, t is not a point, it's a parameter, all right? So I have to plug in that t back into those two original equations that I have. X is equal to t plus 4, and y is equal to t cubed minus 3t, all right? So let's start off with the first one. If t is equal to 1, then x is equal to 1 plus 4, okay, which is going to be 5. All right, and at the same time, if y is going to be equal to 1 cubed minus 3 times 1, so that's going to be 2, or negative 2, excuse me. So here's your first point where you have a horizontal tangent. And I guess I'll write horizontal tangent. Right, and for the other one, if I plug in t is equal to negative 1, then x is equal to negative 1 plus 4, which is going to be 3. And if I plug in that negative 1, see, negative 1 cubed minus 3 minus 3 times a negative 1. So that's going to be 4 minus 1. Excuse me, that's going to be 3 minus 1, which is 2. positive 2. So my other point where I have a horizontal tangent is 3 comma 2. And that's it for that. Okay, so again, we don't have a vertical tangent. We only have a horizontal here. So on example 3, we want to determine the t intervals in which the curve is concave up or down. So notice again, this says the t intervals, right? So this one is going to be a little bit different. Again, how do I know if something is concave up or down? Well, you should know that that's when the second derivative, is positive, then I have concave up. If it's negative, then it's concave down, right? So now we know what we have to do. All right, first of all, I have to take the derivative. So this one's not too terribly bad. Remember, I have to take the derivative with respect to x. So I'm going to write it like, let me write it all. Derivative of sine is cosine. Derivative of cosine is negative sine. Okay, so dx over dy, or dy over dx. dy over dx is kind of important. Right, the derivative of y with respect to x would be negative sine over cosine. Negative sine of t over cosine of t, which is equal to the negative tangent of t. I don't really know if that really helps or not. It might be easier to keep it as sine and cosine, but we'll see. Okay, so what we're going to do here is we're going to take the second derivative, right, and form those formulas. And I guess I can scroll up so you can see it. Know what I'm talking about here. This formula is one I'm going to use. Okay, so the second derivative with respect to x is going to be equal to the derivative. You know what? I'm going to keep it as negative sine over cosine because that's going to be easier for me to plug in the values later. So if you don't mind, I'm going to keep them like that. All of that divided by the derivative of x with respect to t, which is cosine again. Well, except for the derivative of tangent. Oh, gosh. I don't know. I'm sorry. I'm going to keep it as negative tangent again because I want to be able to take the derivative right away. So the derivative of negative tangent is going to be negative secant. So I'm going to come over here now. The derivative of tangent is secant squared, right? Secant squared t over cosine of t. Right, now remember secant is 1 over cosine squared. So really what I have here is the second derivative is going to be equal to negative 1 over cosine cubed of t. Okay. Now, to figure out if, again, so here's where we're going to have to, now we're going to have to do sign analysis, right? So we're going to set that equal to 0, which never happens, okay? So this will not be equal to 0 ever. So that's not really going to be a problem. Now, the other thing we need to check, right, so that's not going to be equal to 0. So the other thing we can do is we need to figure out where this is undefined, right? Where this is equal to 1 over 0, if you will. When would that be equal to 1 over 0? Well, that happens, okay, when the cosine cubed, and essentially I have negative cosine. I'm really just trying to figure this out, right? Now, again, I'm doing a lot of just stuff that really is not calculus at this point. I'm just reminding you of certain things. So I have the cosine of t cubed is equal to 0. So the cube really doesn't matter. It's not going to make a difference. I just have to figure out where cosine is 0, okay? And it has to be between 0 and pi. So hopefully you know right away that the only answer you have is when t is equal to pi over 2, right? Pi over 2, cosine of pi over 2 is 0. Okay, so at that point, I would do sign analysis, okay? Using the second derivative. And I'm only going to check this between 0 and pi. So I don't really care to know anything else. And this is pi over 2. And again, I have to plug this back all the way back here to this derivative, okay? So I'm going to plug in a point that is less than pi over 2. It doesn't really matter what it is, but it has to be less than pi over 2. And if you think about it, a lot of stuff going on, but basically you're in the first quadrant. And the first quadrant, the cosine is positive, but with this negative right here, that's going to make that a negative. Right? And between pi over 2 and pi, the cosine, which would be the second quadrant is always, the cosine is always negative, but with a negative 1 on top, then that's going to make this a positive. Okay, so there's my sign analysis for that. So after doing all of that, again, a lot of trig knowledge there, some algebra for sure, would be that is concave down. Let me zoom in here. It's concave down between 0 and pi over 2. And it's concave up between pi over 2 and pi. Like that. Okay, so that's that for that. All right, there's a couple of formulas that I can explain somewhat, but it might be a little bit confusing until we talked about vectors. I think they probably assume you have at least seen some vectors on here, which I think most of you have not. All right, but this one's not too bad. All right, so basically this is speed. So there's a lot of things to talk about here, but I'll just quickly talk about it. How they came up with this formula, right, is that I kind of learned this from physics more than from calculus, but nonetheless, it's still in calculus, all right? You're going to see this. All right, so if we're trying to find the length of this vector, right, which we call the magnitude of the vector, and let's say that this vector represents some kind of velocity, okay? What we would do is we would try to find the velocity in the x direction, which we can call dx dt, all right? And then we'd also try to find the velocity in the y direction, which is called dy dt. Okay, so to figure out, and I don't really know what you want to call this here. Let's call this, I don't know. Let's call this ds dt or whatever. All right, so to figure this out, to figure out the length or the magnitude of this vector, so that's really what the absolute value symbols mean in this instance, is that to figure out the magnitude of that vector, you would have to then do Pythagorean Theorem. And if you do Pythagorean Theorem, assuming that this right here is what I call ds dt, right? If I do Pythagorean Theorem and that was normally square, and if I take the square root, then you would get that, all right? So if that doesn't make a whole lot of sense, just hang in there, I promise you. We're about to get to it. We're about to do polar coordinates right after this. So anyway, so that's how they get that formula, right? So don't forget that what this means is speed. And speed basically is the speed is the magnitude of the velocity. Basically how fast something is going regardless of direction. Okay, so to find out, all right, so by the same principle, if we want to find out the distance traveled by any object, I can just take the integral of speed, all right? Which leads us into the arc length in parametric form. Okay, specifically, the one we're going to use quite a few times is really either this one or this one. You can see it however you want to, but those are we're gonna use that a lot. Okay, so here's what we're gonna do. So we're gonna use example 4. Now, on this one right here, right, we want to figure out the length of one arc, if you will, and of the, I don't even know how to say that, cycloid, I think. All right, and according to my book, because I did not know that, one arc is usually between 0 and 2 pi. Like that. Okay, so first we're going to have to find dx dt. All right, so we're going to have to take the derivative of this right here. So dx dt the derivative of theta is 1, the derivative of sine is cosine. And for dy dt, let's say the derivative of 1 is 0. The derivative of cosine is negative sine, but it's negative cosine, so that's going to be positive sine of theta, d theta. Well, I don't know what I'm doing. Hang on. I got caught looking at the next step. So anyways, that's that for that. Okay, so remember the formula that we're using is this one. I guess I'll write it in red here. I set the formula. So a to b square root of dx dt squared, that's x, plus dy dt, all of that squared dt, like that. All right, so. Are you busy? Yeah, hang on. All right, sorry about that, guys. That was Miss Howell. She didn't have a little conversation. But anyway, let's move on, all right? So now, all I want to do now is just plug everything into the formula and remember that I'm going to go between 0 and 2 pi and that integral, all right? So I have between 0 and 2 pi, I'm going to square 1 minus cosine theta. dy is going to be sine theta, and I'm just going to square that also. And I guess in this instance, I'm taking the integral with respect to d theta. So since they're letting us use the calculator, you could just plug this in. If you want to simplify this a little further, you can. It doesn't really matter. I went ahead and simplified, but once I realized that I could use the calculator, then I asked myself, why did I just do that? There was no point, but since I did it there, might as well do it here. Just so I can show you my sweet, sweet tricks. This is 1. So this is going to be 2 minus 2 cosine of theta. I kind of overdid this. It's way too big. And now you can plug that in your calculator, and you're going to get 8. Okay? Now, this last one here is actually, it's basically, not basically, it is a physics problem, all right? And they're actually using kinematic equations when I looked at it. So anytime, all right, you have any object that's being thrown at an angle, if you will, you're always going to split this up. And honestly, I'm just kind of nerding out here. You may not need to know this. You basically split this up into its components, all right? So if this is some kind of velocity, then you would just break this down into the velocity in the x direction and the velocity in the y direction, right? Which will come into play here and later, all right? But for now, what they give us basically the position functions for x and the position functions for y, all right? So this will tell me the length and the x direction. That will tell me the length in the y direction, right? And then there are kinematic equations. So all I'm going to do here is I'm just going to use my calculator. And normally we don't use radians in calculus, but I can see why they did it on this one. We only, did I say we don't use radians? I meant to say we normally use radians. We normally don't use degrees, but in this case, they decided to use them, right? So I'm just going to plug in 70 cosine of 50 degrees into my calculator, and I'm going to get a decimal for that. And I'm going to I'm going to go for 5 decimal points. Just try to stay as accurate as possible. And my y value now is going to be approximately, let's see, 2.5 plus 70 sine of 50 degrees is equal to 53.62311 t minus 16t squared. And that negative 16t squared is actually half, or the negative 16 is half of the acceleration of gravity. Okay, so here's what it's asking us, though, right? It's asking us to graph the path of the baseball. Right, now you can put that on the calculator if you want. Actually, I'm trying to think, which one would you put in the calculator? Because we have two functions. Yeah. I think you would put this one, actually. In retrospect, I think that would work just fine, maybe. Yeah. It would look something like this, right? That 2.5 normally is the initial height. Okay. In this case, we're going to call this y, and we're going to call this x. And we're just going to try to graph this, okay? So it says find the difference between the horizontal distance and the arc length, all right? So we're basically trying to find the horizontal distance. Now, for the horizontal distance, all we have to do is figure out the time that it takes to hit the ground, which let's say is right here, right? So there's one thing I have to do, all right? I'm going to have to find time. Now, I know that when it hits the ground, y is equal to 0. All right, so the ground is y is equal to 0. So I'm going to set this equation equal to 0. And then I'm going to solve for t. So you can put that on your calculator, find out where it crosses the x-axis, in this case, on the calculator. And that should get you something about like this. Okay? So my horizontal distance would be equal to x, let me write it as 70 cosine of 50 degrees times 3.39743. Okay, so that's going to give me 152.8678. It tells us, they don't really tell us, oh yeah, it's measured in feet, so this is feet. All right, so again, what I just found was a horizontal distance. Which would be that So this is like 152.87 comma 0. And that point right here would be 0 comma 2.5. Or that would happen if you plug in a 0 for t. Okay, so if you don't know how I got that. All right, so now to figure out it wants to know the arc length, right? And it wants to know which one went further. And it wants to know, well, does it want to know that? It wants to know the difference between the horizontal distance and the arc length. Okay, so I have to figure out the arc length, which I'm going to use the previous formula, right? Which, again, I'm going to write right here. And normally when I encounter a formula that I haven't dealt with enough, I tend to write the formula a few times every time I do a problem because that's the only way I can think of that I can memorize this faster. All right, so there's the formula. So what I have to do is I have to take the derivative, well, let's see, between 0 and the time it hit the ground. All right, so the time it took to hit the ground would be 3.39743. I'm going to take the integral of the derivative of x. So if I take the derivative of that, I would just get 44.99513, and I'm going to square that. Right, if I take the derivative of this right here, notice that the 2.5 would be 0. If I take the derivative of 53.62311t, that would just be 53.6211. And the derivative of negative 16t squared would be negative 32t. So it's almost a constant. I'm going to square all of that. At that point, go ahead and plug it into your calculator. That's going to give you approximately 184.4890. So remember, what I just found was the distance right here, like the distance of the arc length, okay? That's what I just found. All right, so now I want to find the difference between the horizontal distance and the arc length. Again, this is the arc length. So all I would have to do is subtract those two numbers. So I have 184.4890 minus 152.8678. And that's going to be equal to 31.621. All right, so this is 31.61 feet. So the arc length of the baseball is 31.621 feet longer than its horizontal distance. All right. So again, I know that was a long video, guys. I hope you understood it. But if you don't, go ahead and ask me some questions tomorrow, and I guess we'll see you next time.